Well, today we're thinking about standing waves. A standing wave can happen in any kind of a system that has boundaries. Just imagine a traveling wave traveling through that system, and then it comes to a boundary. We know that at any boundary you will get a reflection. The wave will reflect. So now you have both the original wave and, and its reflection. And those two waves, if they've got just the right frequency and wavelength, they'll superpose and create a so-called standing wave. Now you could get a wave with any old frequency and wavelength moving through the medium and being reflected, but you need the right kinds of frequency and wavelength to make a standing wave. The standing wave is significant because it's a resonance for the for that system. Remember what you read way back in the chapter on oscillations. Let's say you've got just a simple mass connected to a spring and it oscillates back and forth at one well-defined frequency. Sometimes it's referred to as the natural frequency. And remember that was the equation was 1 over 2 pi, square root of the k value for the spring over mass. Now, let's say there's some external force that pushes on that mass, and every once in a while it gives that mass a push, or periodically it gives that mass a push. If there's a well-defined frequency to the pushes, then we have the so-called resonance effect. We can make a graph of amplitude versus frequency of the external force doing the pushing, frequency of the external force, and of course that external force might give pushes at any frequency. For most frequencies, if it pushes on the oscillating system, you'll get kind of small amplitudes. But if the pushing frequency is close to the natural frequency, amplitudes get a lot bigger. And the maximum possible amplitude comes when the pushing force matches the natural frequency. Remember also that for any oscillating mass, its mechanical energy is directly proportional to square of the amplitude. That means if wherever the amplitude is a mass is a maximum, that's where the oscillating system will have the most energy. So what and we call this particular phenomenon, getting the big amplitudes at one particular frequency, we call that resonance. Resonance happens because the external pushes are pushing at just the right frequency to maximize the amount of work that that external force does, maximizing the amount of work and thereby maximizing the amount of energy that it gives to the oscillating system. And a large amount of energy shows up, manifests itself as a big amplitude. Same thing happens with standing waves. Except now in a wave system, there are many oscillating things. Right? Say for a wave on a string, every point on the string is a little bit of mass that oscillates up and down as a traveling wave moves along the string. You can still have resonances in a more complicated system like that with many, many oscillating masses. The one difference is that now, because you have many, many oscillating masses, you'll have more than one resonance frequency. That, again, you could imagine shaking the string, vibrating the string at any frequency, and that'll produce a wave. And then when that wave gets to the end of the string, it reflects, and so you have two waves with the same frequency and the same amplitude, all superposing, but for only certain of those wavelengths and frequencies will you get a superposition that gives you big amplitudes. Now, in other words, at just the right frequency, you get a big amplitude. That's a resonance, and in this case, the resonance is a standing wave. Remember, it's a standing wave because we don't see a traveling wave traveling one way. We don't see its reflection traveling the other way. All we ever see is the result of those two waves superposing, and that result is a shape that looks kind of like this. We see one particle along the string bouncing up and down, and then other particles bouncing up and down, and the bouncing up and down is all we see. We don't see any wave shape traveling along the string. So here's 3 snapshots of a standing wave. The solid line represents a moment when all the oscillating bits along that string are at their maximum displacement away from equilibrium. And let's say that's right when I turn on the stopwatch and start watching the standing wave here. Then 1/8 of a cycle later, or 1/8 of a period after this, all these points have been, since they're at their maximum displacement here at time 0, immediately after that they're going to start heading back towards equilibrium, because that's what oscillating masses always do. They come to some maximum distance away from equilibrium, and then the restoring force starts pulling them back. So after 1/8 of a cycle, they've come back most of the way to equilibrium, and then so the displacements at that moment are represented by the dash line. And then after 1/4 of a cycle, every oscillating mass has moved from its maximum displacement back to equilibrium. That takes 1/4 of a cycle. And so at this moment here, every little bit of mass is at its equilibrium position. And of course, most of these points have been speeding up all the time from time 0 to the end of the first quarter of a cycle. So they've got high speeds when they reach equilibrium, and then of course they overshoot until eventually, half a cycle later, everything that was at its maximum displacement away from equilibrium half cycle earlier is now at its maximum displacement from equilibrium on the other side. After half a cycle, all the points that were here are now there, and all the points that were here are now up here. So shouldn't draw any more in that diagram, I'll just draw a new one. So that's the way the string would look if it were not vibrating at all. Every little bit of mass at that moment feels a net force of 0, it's in equilibrium, but then you start the traveling wave, and at one time there every point is at its maximum displacement from equilibrium, and then half a cycle later every oscillating point is at its maximum displacement on the other side. 1/4 of a cycle later. Usually when we draw diagrams for standing waves, the standard diagram is this kind of double snapshot. One curve is the snapshot that shows what displacements are like at one time, and then the other curve shows what displacements are like half cycle later, quarter cycle later. And any oscillating point here will just oscillate back and forth between these limits, because these are, after all, the maximum distances away from equilibrium, amplitude in other words. And that tells us one characteristic thing about standing waves: every location has a different amplitude. They're all oscillating with the same frequency in the same period, but they oscillate with different amplitudes. Here, for a bit of mass right here, that distance and that distance are the amplitude for that little bit of mass, but a little bit of mass right here, that smaller distance is the amplitude. And then for points like this, the amplitude is 0. Points like this actually don't oscillate at all. It's one of the characteristic features of a standing wave. There are points that don't oscillate. We call those nodes. And the points in between a node where you get maximum amplitude are called antinodes, just sort of the opposite of nodes. The existence of nodes is actually the reason why you rotate the food inside a microwave oven. The microwaves that heat the food are standing waves. And so, of course, the standing waves that fit inside the microwave will have different spots of 0 amplitude. And remember, amplitude corresponds to more amplitude means more energy. 0 amplitude means 0 energy. So a little piece of food right here or a little piece of food right here would never receive any energy, would never warm up. And so you'd have, if the food that you're heating up just stays put, there'll be parts of the food that are nice and hot, right? The ones that were near big amplitude regions. Big amplitude means more energy. And there'll be parts that are cold because they didn't get any energy. 0 amplitude means 0 energy. So you rotate the food so that any parts of the food that are at a node at one moment won't stay at a node for the whole time. They'll move into other they'll move to other places inside the microwave oven where there actually is an amplitude, so there actually is energy that can be given to the food, and it heats up evenly. One important feature of the nodes, as mentioned in the reading, and there are several figures there that illustrate this point. Every node is a half wavelength away from the next node. That distance there node to node is half a wavelength, where wavelength just means the wavelength of the traveling waves that combined to produce this standing wave. And that's the key that tells us what the resonance frequencies are for the resonance frequencies that will give us standing waves with big amplitudes. So let's see what the rule is for figuring out what those resonance frequencies are. Just imagine the simplest kind of standing wave that you could get on a string. Say on any musical instrument, guitar, piano, the string is tied down at the two ends. The two ends never vibrate, so the two ends are always nodes. And so the simplest standing wave, there's the string when it's not vibrating. The simplest standing wave would be one in which there are no nodes, no other nodes in between the two ends. So at one time, all points on the string are displaced like this, and then a half cycle later, they're displaced like that. And we'll say that the total string length, we'll just call it plain old L. Node to node is half a wavelength. So in this case, the whole string length is half a wavelength. Or the wavelength is the wavelength of the traveling waves that produce this is 2 times the string length. Now use the basic relationship for a traveling wave. Wave speed is frequency times wavelength, or frequency is equal to wave speed over wavelength. So this is the right wavelength to fit this standing wave onto this string. So this wavelength, put it in that slot, and the corresponding frequency will be a frequency at which you could shake this string and produce a standing wave, produce a vibration with the biggest possible amplitude. So that frequency then is just wave speed over wavelength. Wavelength is 2L. That, as you'll see in a minute, that turns out to be the lowest frequency at which you can shake the system and get a standing wave. So we'll call it frequency 1. Now imagine the next most complicated, just one step more complicated than that simple one we looked at a minute ago, which had no nodes between the ends. Now imagine a standing wave that has 1 node between the ends. And that is, at one point in time, a snapshot would look like that, and then half a cycle later, a snapshot would look like that. Same length of the string. Now we see that node to node, which is half a wavelength, is half of the string length. Or, to put it another way, 2 half wavelengths equals the string length. First half wavelength, second half wavelength. And let me rewrite that as an equation for the wavelength itself, and I'll write it in what looks at the moment to be kind of a funny way, but it'll make sense in a minute. 2 divided by 2 times L. Right? And for this standing wave, the wavelength is equal to the string length, but I'll write string length as 2 over 2 times string length. So, go back to the fundamental relationship. Frequency is wave speed over wavelength. there's wavelength. So the wavelength is 2L over 2. But when you've got 1 over 2 in the denominator, that's the same as putting 2 in the numerator. So now you see that this frequency is twice this frequency. This is the lowest possible frequency where you could get a standing wave. This is twice as high, and so we call it frequency 2, standing wave frequency 2. And I wrote this as 2 over 2 to make the comparison as easy as possible. Now, you've got when I write the wavelength this way, we've got a 2L in both denominators here, so then it's easy to see that this frequency is twice this frequency. Now we'll look at one more, and then we'll see the pattern. That standing wave had one node between the ends. Now how about one with 2 nodes between the ends? So a snapshot at one moment when everything was at its maximum displacement from equilibrium looks like that. Half a cycle later, everything looks like that. So node to node is half a wavelength. So there's 1, 2, 3 half wavelengths in this case. 3 half wavelengths equals the string length, or the wavelength is just 2L over 3. Rewrite F2 up here. So now the frequency is just the same old wave speed divided by this wavelength, which is 2L over 3. And that's 3 times the lowest frequency, so we call it F3. Now you see a pattern. Every one of these higher frequencies is just an integer multiple of the lowest frequency. This is 2 times the lowest frequency, this is 3 times the lowest frequency, and all other resonance frequencies that would give you standing waves, they are all integer multiples of the lowest frequency. So we can write that as a general rule. Any one of the frequencies that would give you a standing wave is identified by some integer. Right? In this case, I just did the first 3. This M is just our general algebraic symbol for integer. M could be 1 or 2 or 3 or 4 or any higher integer. And this is just an integer multiple of the lowest frequency. The lowest frequency is speed over 2L, and then the integer that you multiply by is M. Right? Here M is 1, so 1 times that. Here M is 2, so 2 times that. Here M is 3, so 3 times. That's the key. And go back and think for a second. M was 1 here, M is 2 here, M is 3 here. Go back and look at the shapes, look at the snapshots of the standing waves that vibrated at these frequencies. For frequency 1, you got a vibration like that. For frequency 2, vibration like that. And for frequency 3, you got a vibration like that. Well, here, node to node is half a wavelength, so there's 1/2 wavelength that fits in that system. Node to node is half a wavelength. So there are 2 half wavelengths that fit in that system. Node to node is half a wavelength. So there are 3 half wavelengths that fit in this system. That number m, in other words, just tells you the number of half wavelengths. It's good to remember that there's actually a physical meaning to this number. This isn't just some integer. That if you shake this string at a frequency that's 5 times bigger than that, in other words, m equals 5, you'll see a standing wave in which 5 half wavelengths are fitting on the string. So, in other words, at one time, when every point is at its maximum displacement, you'd get a snapshot that looks like this, and then half a cycle later, the snapshot would look like this. And on that string, there are how many half wavelengths? 1, 2, 3, 4, 5. And you get a standing wave that looks like this only if you shake the string at this frequency. Now, in a real situation, like a stringed instrument, a guitar, a piano, the actual vibrations are a lot more complicated. The actual vibration is a superposition of lots of different waves at different frequencies. So, in other words, it'll be actually a superposition of a whole bunch of standing waves. Each standing wave is going to make some sound with its own frequency. But the brain, or the ear, hears all those different sound waves at different frequencies, but the brain manages to pick out this one and interprets this frequency as the pitch of the sound. Whenever we say that say a guitar string or a piano string is vibrating at like 256 hertz, what we really mean is that F1 is 256 hertz. Because of the importance of this particular frequency, we call it the fundamental frequency. And then the higher frequencies that are integer multiples of the fundamental we'll call harmonics. But now we can understand a few things now that we have this rule here, and especially thinking about this rule, the frequency that determines the pitch. To write out V, this is the speed of a wave on a string, so let's write out our rule for speed of the wave on a string: square root of the tension divided by mass per unit length. And now a lot of things that you see make sense. If the guitar is out of tune, not sounding the right pitch, that is, this frequency is not what it should be, you get that string in tune by changing the tension, either tighten the string a little bit or loosen the string a little bit. And also, we see that for any particular string, if you leave the tension alone and always use the same string, so mass per length doesn't change either, then the fundamental frequency is inversely proportional to the length of the string. And that's why the guitarist or the violinist will finger string. When you put down a finger, you've shortened the length of string that actually vibrates. Right? You're plucking the guitar down here, and the part of the string that vibrates is only from this end to your finger, even though the string itself is a little longer. So by shortening the length that actually vibrates, F1 is higher, so you hear a higher pitch, a higher note. And that works in general if you, say, compare one instrument to another. A string bass has longer strings, so it will sound lower notes, and then a violin has shorter strings, so it will sound shorter L, so it will sound higher notes. And look inside a piano, you'll see the same kind of thing. You'll see that the really low notes, corresponding to the keys at the left end of the piano, involve really, really long strings, big L, low pitch, and then the strings that correspond to the keys at this end, all higher pitches, much shorter L, so much bigger, higher pitch. And also, when you look inside a piano, you can see that this varies also. The thickness changes. Generally, as you go from the strings that give you high pitches to the strings that give you low pitches, the thickness of the strings increases. So what's going on there? Well, again, if this increases, then the fundamental frequency gets smaller. The pitch is lower. And that we also see the same kind of behavior in a similar system that's not literally a string, but behaves like a string in many ways, the vocal folds in a person's throat. If you're singing a higher note, you sing that higher note because you've adjusted the tension in the vocal folds. You've increased the tension. So increase the fundamental frequency, raise the pitch. And then generally, a male voice will more easily sing low notes, and a female voice will more easily sing higher notes. That has a lot to do with this. The male vocal folds are thicker, so mass per unit length is greater. So that corresponds to smaller fundamental frequencies, lower pitches. Let's look at just one example of this. Let's say a typical guitar string might be 60 centimeters long. And let's say that one particular guitar string will sound a note that has a frequency of 320 hertz. Now you want to play a higher note, so you need to shorten the length that's actually vibrating. You put down a finger somewhere. Where do you have to put down that finger? Specifically, if you want to play a note that has 360 hertz for its pitch, by how much do you have to shorten the string? Well, again, just use what we know about inverse proportionality. That is, in the first case, when you didn't put a finger on the string, so all 60 centimeters of the string was vibrating. That's the pitch you got. Shorten the string by some length, the vibrating part of the string by some length, you get the higher pitch. But well, I should call these like A and B instead of 1 and 2. One and subscripts 1 and 2 refer to like the fundamental frequency, and then and then the number 2 harmonic. Right, the fundamental frequency we know is inversely proportional to the length that's actually vibrating. So in inverse proportionality, when this changes by some factor, this changes by the inverse factor. So in this case, we know the two different frequencies, so we know by what factor the frequency changes. Right? Frequency 2 is just some factor times frequency 1. Increases by 40 hertz, which is 1/8 of this frequency. In other words, if you multiply that by 9/8, you turn this from 320 into 360. So that 9/8 is the factor by which frequency changes. Therefore, length has to change by the inverse factor. The new length, shorter length that gives you the higher pitch, is just inverse factor 8/9 times the original length. So 8/9 is about like 89%. So 0.89 times the original 60 centimeters. And so what kind of a number do we get there? 60 times 0.89, about 53 centimeters. So you want only 53 centimeters vibrating in order to get this higher pitch. In other words, you put down a finger about 7 centimeters away from the end of the string. All right, and then you can try some exercises dealing with standing waves.